Alright, now that we have learned how the informer model works, let's apply this to a real-life dataset. So for this project, I'm going to try to apply this to a financial dataset, even though the original demonstration of informer is for predicting ETT, or electricity transformer temperature. Yes, this model is not specifically designed for financial datasets, but yeah, I just want to see how it performs, how good or how bad. Alright, let's get started. So first of all, we import the basic libraries. And then next we download the model. Okay, so what we just did is cloning the model from this link. Okay, let me show you this link here. Well, the model is available in GitHub, and this is what we're cloning. But if you look at it closely, this is in my repository. So I already forked the repository from this. So this is where the original model exists. And if you also notice this, yeah, so I have made a little change to this model just for the prediction part. That's why I want to clone the model from my own repository. After we clone the model, we change the working directory path, and then we get to the branch where my modification exists. Next, after we download the model, let's load the data. The data source is the US Department of Treasury. I already provided the link here. So this is the data that we want to use, daily Treasury par yield curve rates. On the menu here, we have the type of interest rate data that we want to download. Make sure that it's already correct. For this project, we want to use daily Treasury par yield curve rates. And then for the time period, we can only download the data 1 year at a time. So to get the data that we want to use in this project, I had to download the data 7 times. That is from 2018 to 2024. And then concatenate and sort them based on the dates. I will explain why we use args in more detail when we specify the model, but the important thing is that our data is in dailytreasuryrates.csv. Okay, so basically this cell is for loading the data and reorder the columns. Actually, if you don't want to visualize the data, then it doesn't matter. I just ordered this for the visualization. Okay, and here are the last few rows of the data set. The first column is the date, and then the rest of the columns are the interest rates for various kinds of securities. There are some missing values here, and those missing ones are from the 2-month and 4-month treasury bills. Why is that? Because they were only introduced at a later date. Let's see, they have the note here in the website. Here, the 4-month constant maturity series began on October 19, 2022. So since we download the data from 2018, we have almost 4 years of missing data. And then for the 2-month treasury bill, its first auction was in October 16, 2018. Okay, so to understand this better, let's discuss the securities that the US Department of Treasury issues. Okay, so these are all bonds actually, but depending on the maturity term, they have different names. So for the short-term securities, like the securities which mature in less than a year, they are called treasury bills. And then for the next category, those are the securities which mature starting from 1 year to less than 10 years. They are called the treasury notes. Okay, so like 1 year, 2, 3, and 5, and 7 years. Okay, and then for the 10, 20, and 30 years, they are called treasury bonds, and these are the long-term securities. Okay, now let's look at the time plot of these securities. I just deselect all time plots except for the 10-year because this is our main interest for now. Oh yeah, right, I forgot to mention that in addition to the missing values, the data is only available on business days and observed days. Okay, back to the time plot. Here I sort the color based on the maturity term. So the shorter term securities would get darker colors. We have seen earlier that for the 10-year bond yield, it's orange. It's quite light, because it's already a long term, the third longest among these securities. When we talk about bond yields and the various kinds of securities, we expect the yield rate from the shorter term bonds or shorter term securities to be lower than that of the longer term securities. Right, so we definitely cannot use 1 month time plot or 2 months, 3 months, 4 months, 6 months, and then 1 year. Notice the color that disappeared just now. We cannot use that. Let's select the 1 month yield rate again, because since around 2023, the yield rate for 1 month treasury bill is higher than the yield rate for the 10-year bond. That is inconsistent with the theory, so I don't want to use this to predict the yield rate for 10-year bonds. And that's why I also don't want to use a 2-month and all the other treasury bills. This is the 1 year time plot, and we can see here this is higher than the 10-year. So yeah, let's deselect this as well. And then for 2 years, yep. Okay. See, this part here is higher than the 10-year yield rates. And then for the 3 years also. Okay, and then for the rest of them, well, let's compare it one by one. So this is the 10-year bond yield rates, and then this is the 5-year. There are some parts where the yield rate for the 5-year bonds, 5-year treasury notes is higher. But the thing is that these two bonds have quite similar direction and movement, except for this one. During this period, this one is the largest gap between the two. Let's compare now the 10-year and the 7-year. Alright, except for the gap during this period around 2021, they have really similar values over the years. Even though in this period, the treasury note yield rate for 7-year is higher than the ones for 10-year bonds, the gap is really small. Unlike this one, for example, the yield rate for 1 month treasury bill, the gap is too big. So I think if we want to use this plot, this series, the 1 month treasury bill time series, to predict the bond yield for 10 years, I don't think it will be a good idea. Okay, and then this is for 20 years. Okay, so the color for the 20-year time plot would be lighter this time because 20-year is longer than 10 years. So now we expect the line plot for the 10-year bond yield rate to be always lower than that for the 20 years. And we can see here that it's true. Okay, and this one is for the 30 years. We can see that the rate for 10-year bonds is most of the time lower than that for the 30-year bonds. But yeah, there were some exceptions, like this one, September 27 and 28, 2022. But yeah, after exploring the dataset like this, I want to try to use several features or several exogenous variables to predict the yield rate for the 10-year bonds, namely the 7-year and 20-year. Alright, so the next visualization here, I'm just plotting the autocorrelation and partial autocorrelation of the 10-year bond yield rate. And from these plots, we can clearly see that the time series follows an AR1 process or autoregressive of leg 1. This is because the partial autocorrelation at leg 1 is significant, and for the rest of them, they are not significant. And the autocorrelation is gradually decreasing like this. So yeah, it's a clear sign that the time series of 10-year bond yield rate follows an AR1 process. Okay, for the next segment, I want to show us the partition of our data. In this cell, I'm just getting the data for training, validation, test, and prediction. So we will see the data that's already processed by the model. Okay, let's jump right into this cell. Okay, so our data is partitioned into 70%, 10, and 20%. That's for train, validation, and test respectively. And then for the validation and test datasets, they will add an array that has the length equal to the sequence length. Because of those additions, we will have overlapping in our boundaries. So let me show it here. Okay, I think we can see better using this plot. So our training dataset ends on November 23, 2022, but our validation dataset starts on July 18, 2022. Okay, and we can also see it clearly here that the validation and test set overlaps a little bit. Okay, now time to train the model. On the first line here, for I in range of the iteration. This is for training our model iteration times. And our iteration is 5, so that means we want to train our model 5 times. Each time the model starts a new iteration, they will start training from the scratch. By doing this, we can see how robust our model is. And yeah, that's why I set the iteration to be 5. Okay, let's run this. And the model will be saved in different places, by the way. So for each iteration, we will have a different setting name here. And this setting name will be used as the checkpoint name. The folder in the checkpoints directory. And yeah, that's where the best model will be saved. Okay, so this is from the first iteration. We can see that from the first iteration, the validation loss is already lower than the training loss. Okay, and yeah, it just keeps going like this. Now we're at the second iteration. Okay, the training is all done. And yeah, let's see. This is the informer checkpoints here. We can see that we have 5 folders, 5 subdirectories. And for each iteration, we have the best model in that iteration. Okay, this code, exp.model, is just for showing you the layers that are used in this informer model. So we can learn better about this model. Like for example, inside the informer, there's encoder embedding and decoder embedding. And then in the encoder, we have attention layers and convolutional layers. So the convolutional layers is the self-attention distilling. Okay, and we can also get the size of each layer. Okay, now the next step is predicting. This cell, these lines of codes are just for showing you what happened if we stop training in the middle. Stop our process in the middle after training. And then we want to resume it on the next session. We will need our best models earlier, and we put it into our checkpoints directory and make sure that the arguments of the checkpoints is the same. And yeah, they will load it like this. This is what happened under the hood. Okay, but yeah, we're still in the same session. So yeah, first of all, I'm going to make a matrix of predictions, and I name it as prediction prop because this is from ProbSparse self-attention. And then for each iteration, we set the setting name and we use predict. we will load the model from the checkpoint of that iteration and then get the prediction. Okay, let me show you the result directory here. We have 5 subdirectory under the results directory. And then let's see, from the first iteration, we have several files like metrics, prediction, real prediction, and true. For the prediction and true, they are the predictions and the ground truth for the test set. While for the real prediction, that's the real prediction that we want to see. Okay, now let's see the prediction dates. This is also one of my modification as well, because with the original model, we cannot get the prediction dates, like we cannot extract them. But I modified it a little bit so that we can extract them. So these are the prediction dates, but ignore this. We need this. We still need the first date for prediction, but yeah, we will see in the plotting later that these are the actual dates that's produced. Now we're in the next segment where we want to visualize our training results and test results. First up, I want to show you the metrics file here. This is the metrics on the test set. We have 5 metrics here. This is not my main goal of the project, but I'm just showing you the prediction and the ground truth for the test set. Here we can plot them. This is just one window of the test set that starts from April 1st to April 30. Okay, if we run this again, we will get a different window like this or like this. See, now it's October 5 to 11, November 6th. Okay, next, yeah, I want to show you this where we visualize our attention output. Please note that the attention matrix that we will see is from the first batch, because the ID is 0 here, on the training dataset. Okay, the first batch of the training dataset. We can see that the attention matrix shape of the first layer is 90, and for the second layer it's 45. This is consistent with the theory. Okay, and these are the outputs for the first layer. Okay. In practice, the queries and the keys are equivalent, but for the purpose of understanding these attention outputs, we're going to see the queries as horizontal strips. In this output from the first head, we can see a block of pixels with the same color. I'm pretty sure they are the unselected queries. So in other words, the part which looks like a pixelated image shows us the top queries. Now, brighter color denotes a greater attention on that part. So the first head in the first layer pays more attention on the middle part of the sequence. Okay, and then for the next layer, the brighter color is here. It's in a different place. Okay, and then the next head looks like this. We can see that each head pay attention to different parts of the sequence. Okay, now let's look at the attention output from the second layer. From the self-attention output of the second layer, we can see more pixels covering the output matrix, indicating that the heads in the second layer are more focused on the dominating queries. Like they have more dominating queries than the heads in the first layer. Somehow in this case it looks quite similar. Oh, by the way, this is from the the last iteration, I guess. Yeah, right. We didn't set which iteration we want to get our attention from. But yeah, since we have done our loop earlier, I'm pretty sure that this is the attention matrix from the last iteration. Some heads looks like this, yeah. Okay, so now let's compare our prediction with the ground truth. This is our ground truth dataset that starts from January 2nd, 2025 to March 31st, 2025. Okay, and this is it. The average MSE is 0.043. And let me zoom in first like this. We can see that the predictions are not really robust because they're not really similar. But if we take the average, well, it looks okay. I mean, on some days it looks really decent. Like on the first day, January to 2025, the prediction is 4.6, while the real value is 4.57. But of course, there are some days like this one, January 13, where the error is big. The average prediction is way down here, 4.3, while the real value is 4.79. The only model which could predict this the closest is from the second iteration. I mean the third iteration, prediction 2. On some days we get the right direction, and on some days it's like it's happening weekly that we get a really close prediction. I guess it's still a good idea to take the average of these because we get better results. Okay, so these are the predictions using ProbSparse self-attention. Now let's compare it with the full attention. So to do that, I just need to change one parameter, that is the attention parameter. Okay, I change it to full. Now, using the same code, the setting name will be different. Okay, because one of the blanks here is about the attention. Now the training is done. I'm going to save the predictions in prediction full now instead of prediction prop. Actually, this line is not necessary because of course we will get the same shape. Anyway, these are the predictions from each iteration and the average prediction from the full attention. Here, I also include the average prediction from the ProbSparse self-attention model. I'm going to make that disappear for now. And yeah, let's just focus on this new model's prediction. First of all, the average MS is lower. It's a bit lower. It's 0.03 versus 0.04 earlier. Let's see. 0.043. And this one here, it's 0.035. The margin is little though. And I think this model is more robust because the predictions are more similar. They're quite similar to each other. And just like the prediction from the previous model, we have some very, very decent predictions. The prediction on the first 3 days are good. I mean, there's only little difference between the ground truth and the prediction. And then on some days, we have really good prediction. It's just that with this model, the biggest difference now is on January 7 instead of January 13. Let's look at January 13. In the previous model, the biggest error is on January 13, but with this one, the difference on January 13 is not that big actually. Well, relatively not that big. 4.6 versus 4.79. Yeah, actually, since we're talking about bond yield, the difference of 0.1% is huge actually. But yeah, I mean, I'm saying it's not that big compared to the prediction from the previous model. Okay. Okay, now let's see the prediction again from the previous model and deselect all the other predictions. Okay, so what do you think? Which model do you think is better? And now in the last segment, I'm just going to show you some bonus. I also tried using this model for predicting with different horizons. Okay, the sequence length is still the same, 90, and the label length is also 5. I'm just playing around with the prediction length or the horizon. I'm trying 3 different values here. They are 5 days, 10 days, and 3 months. Okay, so I'm just showing you the final result here. The error for the 5-day prediction is 0.025, and then for the 10 days 0.09, and then for this one it's 0.04, yeah, 0.05. Okay, so surprisingly, the error for the 10-day prediction is the highest. It's 0.09. Let's see the prediction one by one. So this is the prediction with the biggest error, that is for 10 days. And if we zoom in like this, yeah, we can see that it's quite bad. But it's funny to see that actually the prediction for 3 months is better than the prediction for 10 days, because the MSE is 0.05 in this prediction. Well, yeah, the MSE is lower, it's only 0.05, but if we plot it visually like this, I don't think this is any better than the prediction for the 10 days. I already calculated this beforehand. The length of all this is 61. So if we have 61 as our horizon and our prediction and our sequence length is 90, then yeah, perhaps we need more input. We need a longer history to get better prediction. But of course, I need to set the sequence length to be the same, which is 90, to make the comparison valid, right? So yeah. And then for the prediction for the 5 days, it's naturally the lowest, but yeah, it doesn't look really good either. I guess the best looking prediction is still the prediction that we saw earlier, that is from the ProbSparse self-attention or from the full attention. Because with that model, I specify the sequence length to be 4 times the horizon. So yeah, maybe that's the ratio that we need to get, but it's really depending on the case. Okay, so that's it for today's project. Thank you so much for watching. If you enjoyed this content, please consider subscribing to my channel. I'll put this notebook in my GitHub. Yeah, don't forget to give it a like, share it to your friends, leave some comments, and I'll see you next time. Bye bye.